Welcome to the Haas Discover series. In this video, we're dealing with chatter and how to get rid of it. There's a great feature available on all Haas lathes that you may not be familiar with. It's called SSV. SSV is short for Spindle Speed Variation, and when it's activated, it increases and decreases spindle speed continuously, which can significantly reduce the effects of chatter. Let's start up our spindle at 2000 RPM, and let's turn on SSV. Our settings have SSV adding and subtracting 100 RPM from our speed continuously every 2 seconds. And we can hear the spindle speeding up and slowing down. Now we'll turn out the lights and turn on a strobe light flashing 2000 times a minute. Now we can see our chuck rotating faster and slower than our 2000 RPM commanded speed. That's cool, but what do you use SSV for? Well, when difficult cutting conditions cause chatter in your workpiece, SSV can help. We all know chatter is bad, but what is chatter? Describing how chatter starts and progresses during turning can get really complex. In essence, chatter amounts to a resonance that starts between the part and the cutting tool, leading to a vibration. This vibration causes a rough, uneven cut on the part. This uneven surface causes the vibration to intensify, making the surface rougher still, causing the vibration to increase again and on, until the part is screaming and the finish is terrible. Now the workpiece and the tool are vibrating badly, causing the cut to unload and load back up many times a second, spiking cutting force like an interrupted cut. No wonder it's shrieking. If it's resonance that gets all of this started, what if we could stop this resonance from even beginning? That's exactly what SSV is designed to do. Let's look at an illustration of how SSV impacts chatter. Here we have a nice, steady, low-level resonance as our cut is progressing normally. When we encounter poor cutting conditions, the resonance begins to change, and we get that escalating vibration that we just described. This vibration will just keep on increasing and increasing. Now we'll turn on SSV. The spindle speed is now going up and down, and that spindle is spending very little time at that resonance speed, keeping it out of the chatter zone. So, the vibration resulting from the resonance has no chance to progress into chatter. So, how do I use this feature? We use setting 165 and setting 166 to drive SSV. In order to understand these settings, let's take a look at this graph. The middle line represents our commanded spindle speed. SSV setting 165 controls spindle speed variation. We're going to insert a value of 150 here. What this does is, it causes the spindle speed to increase by 150 RPM and then decrease by 150 RPM. On our graph, that spindle speed swing is represented by this blue line. So our value of 150 yields a high RPM of 1650 and a low RPM of 1350. As you can see, the total RPM range is 300 RPM. SSV setting 166 controls the time period, and on our graph, the distance across the curves represents the time for one cycle. In our example, we'll use a value of 12, where each unit equals 0.1 seconds. The value of 12 gives a time period of 1.2 seconds to complete each of those 300 RPM sweeps. Now that we understand the SSV concept a little, let's look at what SSV can do when we're cutting without tailstock support. We're going to turn this 1.75-inch diameter shaft and see where the chatter starts. The shaft is held 7 inches out at an unsupported length to diameter ratio of 4:1. Once we reach a diameter of 1.25 inches, this is where we begin to see chatter. On the next pass, at a diameter of 1.15 inches, We're at a 6:1 L/D ratio, which is well past where we normally would need tailstock support. And indeed, we have some serious chatter. Typically, as the L/D increases, chatter also increases. So let's cut a fresh one of these at that same diameter with SSV on. Let's see if it fixes the problem. We insert the M38 command in our program to turn on SSV. We'll use the SSV values from the earlier example. We had setting 165 set at 150, and we had setting 166 set at 12. Remember, that gives us a 300 RPM swing every 1.2 seconds. We can see that the bar cut using SSV has a much better finish. If we had to cut this part without a tailstock, which we know we shouldn't, SSV saves our part. Let's move on to demonstrate how SSV can extend your capabilities when cutting with tailstock support. We tried really hard to find a combination of material and an insert that would chatter during a tailstock supported cut. And what we found is the ST30 cuts so well under normal conditions it really didn't want to chatter. After several attempts using smaller workpieces, we ended up down at a 1/2 inch diameter on a 10-inch long workpiece with no chatter and a decent finish. Now that's a 20:1 length to diameter ratio, and in 1040 steel, not the freest cutting material out there. We moved to much larger material, and we made the setup less and less optimal, until we found a combination of tooling and material that finally would chatter. Now let's see what SSV can do for us on a couple of compromised setups. First, we cut this 3-inch bar right at the edge of the machine's length envelope. Using compromised cutting parameters and clamping, we got chatter. Major material and setup compromises forced this part to ridiculous levels of chatter. And under normal circumstances, we would have stopped cutting long before reaching levels of chatter like this. And we're not saying you should expect SSV to cure chatter at this absurd level. Yeah, there is still chatter on the SSV part. But looking and listening to the difference between the two shows us that SSV made a really positive change. And if you aren't starting out with horrendous chatter, then SSV can often solve your problem. Okay, let's leave the realm of the ridiculous for a more common set of circumstances. This time we're using a 2.25-inch diameter, mild steel shaft, held 16 inches out from the jaws, still with tailstock support, of course. Our tool geometry is less than optimal, with a larger nose radius. Our slow feed rate is spending a lot of time in the cut, and the support is coming from a less rigid CNC center, all part of our recipe for achieving chatter. With SSV off, we begin to get chatter at a diameter of 1.12 inches. Just to make sure we've got some decent chatter going, we'll take several more cuts until we're down around an inch diameter. Our test bar is now chattering quite seriously. The L/D ratio of this setup is now 16:1. Now let's see how this cut does when we turn SSV on, cutting again at a diameter of 1 inch. So our setting 165 is equal to 125, and we have our setting 166 at 6, giving us a 250 RPM swing every 0.6 of a second. And again, we can hear and we can see the chatter has disappeared. The finish on the shaft using SSV is significantly better than the one running at one single speed. Some people like to run with smaller values than we do here, like a 165 value in the 20 to 50 range, combined with setting 166 numbers between 10 and 30. But here at Haas, we found that the best starting point for these two numbers is a setting 165 value between 100 and 200 RPM, combined with a setting 166 period value between 5 and 20. Some experimentation will probably be necessary to find the best values for your particular part. Now we're going to take a quick look at G96 and G50, two commonly used G-codes that can interfere with the way SSV functions under certain circumstances. We'll start with G96, which is the constant surface speed command. To get a handle on G96, we need to understand the concept of surface footage. Here we have two bars, one 7 inches in diameter, and the other only 1 inch in diameter. Looking at the 7-inch bar, let's see how much distance we can cover cutting for 1 revolution. In 1 revolution, we cover a distance 22 inches long. So 1 revolution equals 22 inches. Now looking at the 1-inch diameter bar, 1 revolution is cutting only about 3 inches. The 7-inch part is covering 7 times more distance per revolution than the 1-inch part. That means the 1-inch bar needs to rotate 7 times faster to cover the same distance. Now let's say we want to use this insert, and it cuts best at a surface footage rate of 900 SFM, or surface feet per minute. That's 900 feet of material rotating past the cutter every minute. To get 900 surface feet per minute on our 7-inch part, we need to cut at 490 RPM. But to get 900 surface feet per minute down at a 1-inch diameter, we have to crank that speed up to about 3,400 RPM. Yep, 7 times faster. So when our part got 7 times smaller, our speed had to get 7 times faster. Now we know that speed must increase as diameter decreases, and vice versa, to keep surface footage the same. And that's exactly what G96 does. It adjusts spindle speed on the fly to maintain a constant surface speed at the tip of the tool. When you're facing a part, for example, spindle speed increases constantly as the cut moves towards the center. So it's easy to see how spindle speeds can get away from you pretty quickly. So it would be good to have control over the high speeds that G96 can generate, and that's where G50 comes in. When used in conjunction with G96, G50 sets the fastest allowable speed within a programmed operation. The spindle can't go any faster under any circumstances. G50 provides a failsafe, and it's wise to include it in your programs. Say we're turning a heavier part, and we're concerned about high RPM reducing chuck grip force and potentially throwing the part. And we're not comfortable going any faster than 2000 RPM with this setup. So all we would do is set our G50 to 2000 RPM. Now the spindle can't go above 2000. G50 is often used in this way to keep G96 commanded spindle speeds in check. Okay, let's recap, and we'll see how G96 and G50 can interfere with SSV. For this new example, we'll use this 1 3/4 inch bar. Now we know that G96 adjusts spindle speed to maintain constant surface speed. Our program has a G96 set to 775 this time, which is telling the spindle to maintain that 775 surface feet per minute. Our program here has G50 set to 3000 RPM again. SSV is on, and our setting 165 value is 200. With 200 added to the commanded spindle speed, our RPM for the first cut peaks at 2000 RPM. As we continue to cut and that diameter gets smaller, of course the spindle speed increases. The final pass is at just under 1 inch in diameter. Now, G96 is attempting to push the spindle to 3150 RPM. Remember, the spindle speed is being limited to 3000 RPM by the G50 command. So we have a problem. The black line rising above the 3000 RPM ceiling represents the part of the SSV range that's being clipped. The blue line below this represents the only portion of the SSV range that's doing anything. So how do we solve this problem? There are only 3 variables that we can change here. We don't want to increase the G50 setting because we're afraid of throwing the part. And we know our SSV settings are allowing for a good finish, so we don't want to touch those. That leaves us with G96 as the logical value to change. In this scenario, we'll reduce the G96 setting from 775 down to 700, which still allows the insert to cut decently. On our chart, you can see the G96 range drops down And now our peak RPM with SSV is 2900 RPM. We're below our G50 limit, and SSV is working again through its entire range. How can I tell if G96 and G50 are causing SSV not to function or to clip? Easy. You won't see the spindle RPM change that much on the screen. And you also wouldn't hear the spindle changing speed continuously. Remember, if you can't hear it working, it probably isn't working. Here's an example of what it sounds like when SSV is fully functioning. One more tip before we wrap up. You should pay close attention to how SSV settings affect spindle load. Extreme RPM swings and short time period values can push the spindle well into the overload region. Starting with SSV values of 50 and 20, we see the spindle isn't really working very hard. Change those values to 110, twice the speed in half the time, and now the spindle load is at a moderate level. Increasing those values to 205, doubling and halving our values again, now the spindle is really working. In this region, SSV should only be run for very short periods. There will be situations where L/D ratio, materials, and cutting parameters reach such an extreme that even SSV will not be able to remedy the chatter. But there are also times it can be the difference between completing a job or not. SSV is a valuable tool for achieving the best finish on a difficult material or setup. Thanks for watching.